All right, this is lesson 3.2 on differentiability. So you may notice that your graph is differentiable. That means that is lesson 3.2 on differentiability. What is differentiability? It is saying that when is a function differentiable, meaning when does a function have slope? So when we talk about differentiability, it means that is this can we take the derivative of this function? Is this differentiable? Does it have slope at the segment that I'm looking at or in the entire function, right? So right now we're looking at when does it not work? When do we not have derivative? When do we not have a slope for the function, right? So there are some cases that you don't have the slope for the function. For example, when you have what we call a corner, right? So when the function is an absolute value function, an absolute value function looks something like this, right? It's a v. Now, why does it not have a derivative? Well, on the left-hand side here, the derivative is -1 because down one, right one, down one, down one, down one, right one, consistently, no change. It's -1 all the way through up to that 0. Then on the right-hand side is positive 1. It's up and right 1, up and right 1, up and right 1. It is positive 1 all the way up to infinity, right? And no changes. But here at this point right here, what is it? Because it went from -1 and then very quickly it went to positive 1. And then there's nothing in between. There is no negative 0.00005. There's no negative 0.000 whatever. And there is no 0.0002 and then there's no gradual change. It is a sharp change. So when it's that sharp of a change, there is no derivative at that point. So only at x equals 0, right? So at x equals 0, it is not differentiable. A second type is called a cusp. So it says the slope of a secant line approaching infinity from one side and negative infinity from the other side, an extreme case of a corner. So what does it look like? So we use this example of x to the 2/3. Now, your graph looks something like this, like a square root function and its mirror image, right? So it is approaching negative infinity from one side. I mean, they're both approaching infinity. So this graph is going vertical down, and this graph is also heading vertical down, right? So it is creating that that very extreme slope, and there is no gradual change from one to another. Again, very similarly to the absolute value function we have in number 1. So that is a cusp there. A lot of times, tests and quizzes will use these two very interchangeably. So a cusp and a corner, they don't really distinguish the difference between those. So as long as you have a sharp turn or a sharp change in your derivative, you can just go ahead and call it a cusp, and that's totally okay. All right. A third type is what we call vertical tangent. A cube root of x looks something like this. It's the s function, right? Now, why is this a vertical tangent? So your graph is gradual. Notice I'm breaking into small increments. But then as it gets to this point, your tangent line is actually a vertical line like so. Then it tapers out again to match. Again, I'm going to zoom in for you. It tapers out again to show you the slope at the other segments, right? So this point right here, it is creating a vertical tangent. And same thing. So all of these, all these have a problem at x equals 0. Nowhere else in the function. Nowhere else does it have a problem. It's only at x equals 0. So same thing here. This is a very famous function. This is a very, very widely used function. At x equals 0, what is the problem? Well, if you plug in your t-table, you will see. You plug in any positive value, you're going to get 1. So it's going to get 1, 1, 1, 1, 1, no matter what, because you have the same value over the same value, and it's positive. But if you plug in negative value, you're going to get -1 because this value is going to make it negative. So it's -1, -1, -1. But if you plug in 0, you're going to get 0 over 0. So there's nothing there. So this graph is broken up. It's discontinuous. So there is a problem there when it's not continuous. Therefore, there is no derivative. There's no slope when there's no continuity. So right here, I'm trying to remind you that if a function is continuous, so in examples 1, 2, and 3, it is continuous, but it's not all differentiable. There are places where it's not differentiable, and especially those vertical tangents and cusp and corners, right? If a function is differentiable, if you know it is differentiable, it implies that it is continuous. It is always going to be continuous, because to have differentiability, you have to have continuity, right? And then, therefore, the last bullet point here is if it's not continuous like it is in number 4 here, then it's not differentiable. So the continuity is a must. for it to be considered differentiable. Then you look at the different cases to see if it is truly differentiable, and then there is a possibility that it's not because it is a vertical tangent or a cusp, and then it is differentiable because it is continuous. Okay. All right, so theorem 2 here is the intermediate value theorem for derivatives. Sometimes it's shorthanded as IVT. So it does say that if the A and B are 2 points on an interval on which f is differentiable, so you know that this differentiable, this is A to B, right? And this could be any weird shape in between. You know it is differential between. So that it says f prime takes on every value between f prime of A and f prime of B. That means you can find f prime in everything in between A and B, because you know that this function is differentiable. Okay. All right. So next, it says using one-sided limit, show that the function does not have a derivative at x equals 0. So first thing you want to do is graph this out. This is a piecewise function. So a square root function for the first piece for x is greater than or equal to 2. So square root starts at 0, 1, 4, square root of 4 is 2, square root of 9 is 3. So here's my function here. And then negative 2x on the other side. So coming down to negative 2, coming down negative 2, oops, not 1. All right, so here's my function, all right? So we are going to go ahead and look at the left side first, coming from the left. We'll look at the derivative from the left side first, all right? So we are going to say the left side, limit as x approaches 0 from the left side of this derivative. So 2 times, negative 2 times x plus h minus the function negative 2x all over h. So we're going to work it out to be limit as x approaches 0 from the left-hand side, negative 2x minus 2h plus 2x all over h. These two cancel out. The h's should reduce out. My left side derivative is negative 2. So that's a derivative on the left side is negative 2. Okay. On the right-hand side, so limit as x approaches 0 from the right-hand side, we have square root of, all right, we have the square root of square root of x. So you're going to go ahead and plug in x plus h minus square root of x all over h. So this is where I remind you of a nice tool you have from before. It's called Conjugates to try to clean this up. You multiply it by the opposite of your square root. So square root of x plus h plus square root of x. All right. You get limit as x approaches 0 from the right-hand side. You the function of a conjugate is that you get a squared minus b squared. So you get the first term squared, which gets rid of the square root, so x plus h, minus the second term squared, which gets rid of the square root, so just x, all over h times square root of x plus h plus root x. All right, so these two canceled out. The h's reduces out, so you're left with limit as x approaches 0 from the positive side, 1 over root x plus h plus root x. Okay, so then limit as, sorry, I keep putting x here. It's h approaching 0. So h approaching 0 from the positive side. Apologies here. H approaching 0. All right. So the h's are gone, right? So you plug it in the h, you get 1 over root x plus root x, which is 1 over 2 root x. All right. So then we're going to plug in our value. So we're looking at the derivative at x equals 0. So we plug in a 0 and we get, so x equals 0 at x equals 0. You get 1 over 2 root 0, which is 1 over 2 times 0, which gives me 1 over 0 again. So this actually isn't undefined. You're looking at the limit as x approaches 0, right? You're trying to get as close to 0 as possible to find the derivative at that point. So as this number is getting closer and closer to a small 0, as it gets smaller and smaller, approaching 0, you're really getting a big number, right? Think about how you're dividing. If you go 1 divided by a half, you get 2. 1 divided by a third, you get 3. 1 divided by a tenth, you get 10. The smaller the fraction, the smaller the number you're dividing by, the bigger the number turns out to be. So if this is getting close to 0, my final answer is going to be as big as infinity. All right. So that's not really the main point. The main point is to remind you that, hey, my left side is not the same as my right-hand side. So if they're not the same, then this graph does not have a derivative at that point because it's a piecewise function. The two derivatives have to be the same for it to be continuous, and it has to match up, right? So we have further proved that it doesn't have a derivative at that point because the two slopes, the two derivatives separately from the left side and right side do not match up to each other, right? So you go ahead and say the left limit does not equal the right limit. Therefore, it's not differentiable. At x equals 0. Okay, that's it.